This section is about dimension and rank. So let's recall from the previous section that a basis for a subspace of Rn is a linearly independent set within H that spans H. So again, a basis is a set of vectors that is linearly independent and spans. And each subspace H of Rn can be characterized by its dimension. So the dimension is just defined to be the number of elements in your basis set. Exercise 1 says find a basis for the subspace H spanned by these three vectors. So the question is, are these independent and do they span all of R3? So let's augment and row reduce. While I'm row reducing, I see that I will have 3 pivots, which tells me that they will be linearly independent. So because all 3 of these are independent, all 3 of those will make up the basis. The basis for the subspace that is spanned by these 3 vectors is these 3 vectors themselves. Because there are 3 vectors in my basis, the dimension is 3. Because my vectors are in R3 and my dimension is 3, that really means that these 3 vectors will span all of R3. So in other words, to be a 3-dimensional space in R3 means you are the whole space. Exercise 2 is the same thing. We want to find a basis for the subspace that is spanned by these 3 vectors. And we want to determine if there's any dependence relationship, or are they all independent and they span R3. This is fairly easy to notice if you just take a second that this V3 is the same as V1 plus V2. That tells me V3 is dependent. So that tells me that if I want a basis for this subspace, I would just take the first 2 vectors because your basis has to be independent. So here my dimension is 2. Because there's 2 vectors in my basis. Visually, this would be a plane in R3. Exercise 3 asks, could R3 possibly contain a 4-dimensional subspace? And the answer would be no. R3 can only have subspaces of dimension 3 or less. So some important observations. The space Rn has dimension n. Every basis for Rn consists of n vectors. A plane through 0 in R3 is a subspace with dimension 2. A plane has 2 dimensions, and a line through the 0 vector in R3 is dimension 1. In the previous section, we talked about column space and null space. Recall that the column space is the set of all linear combinations of the columns. The dimension of the column space of A matches the number of pivots. This is also called the rank of A. So the rank is the dimension of the column space. The null space of a matrix is the set of all vectors that map to 0, and the dimension of the null space is the same as the number of free variables, and the dimension is referred to the nullity. So if the rank is the same as the number of pivots, and the nullity is the same as the number of free variables, those 2 together will add up to the number of columns. Exercise 4 asks us to find the basis for the column space and the null space, and then state the rank and nullity of the matrix. So a little bit of review from last time. Remember that to find the basis of the column space, we identify the pivots. So the first 3 columns have pivots, which means the basis for the column space of A is the set of vectors 1, 5, 4, 3, 2, 1, 6, 4, and -4, -9, -9, -5. So it's the first three vectors. Really what that tells me is that the last two vectors are dependent on the first three. To find the basis for the null space of A, we need to do a little bit more work. I'm going to augment my reduced form with zeros. I see that x5 and x4 are free. And then x3 is the same as x5. x2 is negative 2x4 minus x5. And then x1 is 0. Again, if I rewrite this as some column times x4 plus some column times x5, those will be my basis elements. So x4, the coefficients would be 0, negative 2, 0, 1, 0. And for x5, it's 0, negative 1, 1, 0, 1. So the basis are those two vectors. The rank is the dimension of the column space of A, and that is 3 because there are 3 vectors in the column space. The nullity is the dimension of the null space, and we have 2 vectors in the null space of A, so this is going to be 2. Theorem 14, referred to as the fundamental theorem of linear algebra, so kind of important, just says that the rank plus nullity is the number of columns. Remember that the rank is the number of pivots, and the dimension of the null space is the same as the number of free variables, so those two things together add up to the number of columns. That's all that theorem is saying. So in exercise 5, suppose we have a 4 by 7 matrix, so this is our number of columns, and A has 3 pivots, so if there's 3 pivots, that tells me the rank equals 3. It says, is the column space of A equal to R3? And then what is the dimension of the null space? So I'm going to do the dimension of the null space first because that's easy. That's just 7 minus 3, which is 4. There's 2 things I need to check for the column space of A. I do know that it has dimension 3, and so does R3, so the dimensions match up, but I want to make sure the columns live in R3. So our columns length 3. So this is no. So because I have a 4 by 7, I see that my length is R4. So I cannot equal R3 if I'm not in R3. So my column space is a 3-dimensional space in R4. Exercise 6 asks, what is the rank of a 10 by 17 matrix whose null space is 8-dimensional? So I know that rank plus nullity equals number of columns, so 17. I know that my nullity is 8. So just by subtracting, I know that my rank is 9. In section 2.3, we had a big list of equivalencies, and now that we know a little bit more, we can add to this theorem. So again, this is the invertible matrix theorem, and we know that if A is invertible, then we know the columns of A form a basis for Rn. We also know the column space of A would equal all of Rn, and the dimension of the column space is equal to n. The rank is n. The nullity would be 0, and the dimension of the null space would be 0. All of these can be added on to our big list of equivalent things to a matrix being invertible.